Hello, I'm Dr. Amy Smith, a principal investigator at my university. Right now, my team and I are working on diabetes research. I need to design and conduct research that generates high-quality data and reproducible results that my team and I can publish and use to secure crucial funding for future studies. The work we do is important. There are millions of people worldwide counting on me and my team to make the next discovery that leads to a cure for diabetes. By 2030, it's estimated that 366 million people will have type 2 diabetes. That's over double the amount of people who had it in 2000. For the investigation of the electrophysiological properties of islets of Langerhans, which are key in the field of diabetes research, the only approach is to use the patch clamp technique, which requires individual cells versus complete islets. Sounds simple, but it's highly technical and limited in scope. We can look at only one cell at a time. The recordings are invasive. Not only is it less than ideal to perform, but it also does not allow for long-term recordings and cell network communication. Also, there is no high throughput, which is essential for pharmaceutical screening research. What I really need is an easier way to conduct my research that places analyzed data at my fingertips. I need to see the islets intact and do long-term, real-time electrical recordings directly correlating to insulin secretion, especially to evaluate a drug's effectiveness over time. And luckily, I found the solution that checks off all these boxes. Invented by a group of researchers who worked closely with MCS, a division of Harvard Bioscience, BetaScreen provides non-invasive electrophysiological recordings from intact islets of Langerhans. As a researcher, this is a game changer. Before the islet can release insulin, channels in the membrane open and exchange ions. The resulting current flow leads to a change in the membrane potential. This signal is recorded with BetaScreen real-time while the islet regulates its insulin secretion. Instead of piercing a cell membrane like we do for a patch clamp, the intact islet is pipetted onto the flat microelectrode array. A suction trap mechanism captures the islets directly above the electrode automatically. Voltage changes are recorded as real-time parameter of the islet activity, the step in which insulin secretion is precisely regulated in the pancreas, depending on blood glucose abundance. The best part is, we can say goodbye to performing technical procedures for only one cell at a time. BetaScreen can record up to 40 islets simultaneously. After the information is recorded, it's sent to the software where the analysis happens. With its user-friendly drag-and-drop flowchart design, BetaScreen becomes an integrated analysis tool that allows us to visualize long-term experiments with islets of Langerhans. After I hit record, BetaScreen starts to look for spikes and bursts for specific analysis that indicate dose response as well as the various phases of the experiment. This means I can take my diabetes research to the next level with the ability to either use the predefined setting or manually adjust them to be specific to unique research needed. It even exports the reports to user-friendly programs like Excel. BetaScreen is easy to learn, easy to use, and provides the opportunity for better diabetes research. And that means I'm one step closer to publishing our results and securing funding for future research, all resulting in important science that can help millions of people around the world have a better life. To find out how BetaScreen can help your diabetes research and for information, please visit our website or contact our sales team for a live demonstration.